In this video, we will look at a problem that requires very sharp observation skill, but it is an interesting problem nonetheless. You are given an array containing of n positive integers, that is, each element of the array is strictly greater than 0. Then you are allowed to do a series of operations on it, and in one operation, you pick any three consecutive indices, basically a subarray of length 3, and you call that as a triplet, and suppose the values of the triplets are a, b and c. This is the first element of the triplet and this is the last element of the triplet. Then you check whether this condition is satisfied, that is, the first and last element of the triplet should be strictly greater than the middle element, and if this is indeed satisfied, then you can replace this triplet, that is, you can delete all these three elements of the triplet and you can replace it with a single element whose value would be a plus c minus b. Now notice that there is no restriction on the order in which you have to process these triplets. So you can process this triplet in the first round, or you could have also processed this triplet x, y, z in the first round. Now, of course, the order in which you process the triplets will matter, because if you do not do it in an optimal way, then it is possible that after some point of time, you are left with an array in which none of these triplets satisfy this condition. And the problem asks you to find that if you were to do all of the operations optimally, that is, if you decide what order in which to do the operations, what is the smallest length of the array that you can achieve. Because notice that each time you do the deletion and then reinsertion, the length of the array reduces. So of course, there will be a theoretical minimum length that can be achieved, and you have to find out the length given a certain array as an input. So how do we approach this problem? So to think about this problem, we'll do some rearrangement and we'll look at some observations which might be trivial to some but might not be that intuitive to others. So first we start out with this observation that if the triplet that you're dealing with is A, B and C, the original constraints says that A plus C should be strictly greater than B. Now let me rewrite it in a fancy way like so. A plus C minus B is strictly greater than 0. And let me rewrite it in another fancy way, which is A minus B plus C is greater than 0. Now what is the motivation behind writing it in this fancy format? Because mathematically this and this is equivalent. But you will see why this interpretation will help us a lot more in solving the problem. And why is this helpful? Because in this interpretation, all the elements of the triplet, they appear in order. First A, then B, and then C. Now, the condition that you have to check is this one, that A minus B plus C should be strictly greater than 0. And what is the replacement that you have to do? You have to replace it with A plus C minus B. In other words, if you do a fancy rearrangement, you can see that it is nothing but A minus B plus C. This means that you are checking for this condition and then replacing it with the same thing that the condition was checked for. This means that you only do the replacement if the incoming element, this is the incoming element, if this is strictly greater than 0. So what is the first observation that you can make from this? So we are already in the territory of making some observation. So you see that if the array started out with the positive integers, then after each round, the array will still contain positive integers only. So we can make that observation. The array will contain positive integers. And why is this true? Because by definition, you only pick the triplets such that their incoming element is strictly greater than 0. And if it is, then you remove that triplet and you replace it with the incoming element, which of course would be greater than 0. So this is one observation that we have made so far. Now what is the second observation? So second observation, you can notice that how does the length fluctuate. So in one operation you are removing two elements and then adding one element of the triplet back. So if you do the operation here A, B, C, then you see that you are deleting A, you are deleting B, and you are deleting C, and then you are inserting this value A minus B plus C. So this means you removed three elements, but you added one element. So this means the length will decrease exactly by 2 in each operation. So what is the second observation that we can make is that if you start out with length L, then you can notice that the length of the array decreases by 2 after each round. So what does this tell us? So you can see that we can already make some interpretation about the final length. This statement says that the length can only decrease by 2. So if a quantity can only decrease by 2, if it can only go to x minus 2 or x minus 4 and so on. So if you apply a fancy trick over here where you take modulo 2 on each of the intermediate length. So you can see that if you take the modulo 2, this would be x modulo 2, and this would still be x modulo 2. Why? Because 2 modulo 2 is 0. And this would still be x modulo 2. This means that the parity of the length does not changes. So you can make another conclusion that the parity of the length does not change. So if you had an odd length subarray, if you had an odd length, what is the minimum length that you could achieve? In theory, that is 1. And if you started with an even length, what is the minimum that you could achieve? That is 2. But 1 and 2 might not always be achievable. So let's see what are the cases in which these 1 as well as this 2 will always be achievable. So how do we find out like which cases it will be achievable and which cases it will not be achievable? Now notice that the order of the operations does matter, because if you do the round 1 on this triplet, then it is possible that after doing the replacement, this will cause all the future triplets to be blocked, because they will now compare. So look at any triplet that includes this element. So if this is the first element, then this incoming element, which is a minus b plus c, this is the second element and this is the third element. So what if doing this operation at the start negatively affects this too and prevents us from doing any operations further? So we have to be smart about the first choice that we make. But how do we find out what is the smart choice and what is not? So let's think backwards. So this is another technique that we use. So I'll write it like so. You think backwards, and this time let me remove the problem statement and add all the observations on the top. So now we are trying the strategy of thinking backwards, and if you are thinking backwards, then you will eventually, suppose you apply any random strategy, so you will eventually reach an array that looks like this, contains some value a, b, c, d, e, f and so on, and assume that from here this point onwards you are not able to make any operations. So what does this mean? This means that this is the minimum length that you could achieve via your strategy. But why are we not able to make any operations? This would mean that this first window cannot be operated upon. This would only be possible if a minus b plus c is less than or equal to 0. But if you are not able to do any operation, then the second window should also not be operable. So you could say that b minus c plus d should also not satisfy the greater than or equal to 0 constraint, because if it is strictly greater than 0 constraint, that you could have simply done the operation. But now if you notice that this is a number that is left side is a negative number, right? And the right side is also a negative number. So if you sum up two negative numbers, you should also get a negative number. But what happens when you sum it up? This and this cancels out, this and this cancels out. So the left side is a negative number, but is it actually true? Notice that this A is a positive number from the array and D is also a positive number. So this means that the LHS is a strictly positive number, but the RHS says that it should be a less than or equal to 0 number. So this means that it is always, as long as you have 4 elements A, B, C and D, this argument will always hold. So now you can claim that this is another observation that you can make. It is always possible to do the operation if length is greater than or equal to 4. So no fancy tricks required over here. So previously it looked like that the strategy would matter and whatnot, but now we are seeing that the strategy actually does not matter. You can, as long as the array has 4 elements A, B, C and D, then you can always do these operations. But there was one caveat that we missed when we were making this argument, that is A minus B plus C is less than or equal to 0 and B minus C plus D is less than or equal to 0, and then we made the argument that A plus D is less than equal to 0 is a contradiction. One thing we forgot, that A and D might not necessarily be elements from the original array. So they might not necessarily be strictly greater than 0. So this is not obvious why we are saying that A and D are strictly greater than 0. And that is when you will realize, if you have good observation skills, you will realize that previously we said that you are replacing any positive integers with A minus B plus C, but you are only doing this replacement if the incoming element is strictly greater than 0. So we had made this observation, right, that after every operation you will have all positive integers only. So even though this A and D might not originate from the original array, but our arguments still hold, because at any given point of time the array will still hold all positive integers only. So you can conclude that it is always possible to do these operations as long as the array length is greater than or equal to 4. So now we only have to worry about how much can we reduce it down further. Then we also said, we had also made another observation, that the parity of the length does not change. So let's list that down explicitly as well. The parity of length does not change. This means that if you start with length even, if the original array had an even length, then the final array cannot be of length 3 or 5 or 1. So this means that the theoretical minimum that you could achieve is 2. And we just said that no matter what operations you do on the array, no matter in what order, you can always bring it down to something that is less than 4. And how can you do that? Every time you reduce it by 2 by doing any valid operation, and you know that any valid operation can exist. In fact, any valid operation will exist in this 2 window only. One of these 2 window will always be a valid operation and you should be able to do it. And as soon as you reach a length of 2, one of this length of 4, one of this windows would be valid, and you can compress it down to length 2, which is the theoretical minimum, because you cannot go from 2 to 0 because you need a triplet to do the operation, and you have just achieved it. So the length is equal to even case is not very interesting, because you know that length 2 is always achievable for even length array. So in fact, let me formalize that. So for even length array, you can always achieve the minimum length is 2. And here you can see that the ordering does not matter. So now the only interesting case is, what if the original array is of odd length? So we are dealing with this case that the original array contains odd number of integers. Then from the previous arguments, we said that you can always keep on doing the operation as long as the length is greater than equal to 4. And we also said that the parity of the length does not change. This means that at some stage you will reach length 5, and then since 5 is greater than or equal to 4, you can still do an operation and you can reach length 3. Now on length 3, our arguments are not transferable to length 3, because whatever the two window argument that we made, like these two overlapping window argument that we made, that was only for 4 elements. But if length is equal to 3, then you are at the mercy of the elements that remains, that are they able to make sure that the final elements that are retained, are they strictly greater than 0? If yes, you can compress it down to length 1 by doing this operation once and replacing these 3 integers with just a minus b plus c. But if the final sum that remains, which is a minus b plus c, if it is less than or equal to 0, then you cannot do this operation. So this means that you only have to do the operations in such a way that you can make sure that the final a, final b and final c that remains, this sum, like a minus b plus c sum, this has to be greater than 0. So let's see how we can ensure this, because if we can ensure this, then we know that 3 is always possible. What all we have concluded so far, we know that 4 is possible, so 2 is also possible. So for even length, you can blindly say that all arrays of even length can be converted to the minimum length, which is 2. But for odd length, all arrays can be blindly converted to 3, no doubt about that. But the jump from 3 to an array of length 1, that is the tricky part. Some arrays can be converted and some cannot. So we want to find out what are the special properties of the array that can go from length 3 to length 1. So to do this, we'll look at the quantity that is preserved at the end. And at the end, you just want to have 3 elements. You want to have A, B and C. And what would you compare? You would compare this A minus B plus C. So now you can apply some observations and you can notice that what is this quantity really? With these 3 elements, this is nothing but your alternating sum, plus, minus, and so on. So let's formalize this. This is your alternating sum. So then you might get an idea that what if we explore what happens to the alternating sum of the original array after you have done the operation. So suppose the elements in this array are A, B, C, D, E, F and G. This is the original. Then what is the alternating sum of the original array? You can see that it is A minus B plus C minus D plus E minus F plus G. Right? Now, what happens when you apply the operations? So suppose you have applied the operation arbitrarily on C, D and E. So the new array would be A, B and then C plus C minus D plus E will be a single element, C minus D plus E, and then you would have F and G. But notice that even though it is a single element, the insides of it already looks like an alternating sum. So when you create the alternating sum of this, it would be A minus B plus C minus D plus E minus F plus G. So you see, this alternating sum did not change. But this is for the case when you started your operation that had a plus corresponding uh, to it when it joined the alternating sum series. But what if you had started an operation which had a minus? So suppose you had done the operation on D, E and F. Then after the operation, the elements that would be remaining, if you focus on it, it would be A, B, C, and then D minus C plus F would be in a separate bracket, D minus C plus F, and then you would have G. But what is the alternating sum of this? So you can see that it is A minus B plus C, and now this entire box needs to go into the negative section because you are considering an alternating sum on the elements that remain. So this is plus, this is minus, this is plus, and this entire box is minus. So this would become minus D plus E minus F plus G, which is surprisingly the same as the original alternating sum. So we have made a very big discovery, which is that the alternating sum is what's known as an invariant. So in these kind of problems, even though there is no rule book or playbook to solve these kind of problems, some techniques that you could use is try to find some invariants. So you will realize that we already found some invariants, which is the parity of the length that was an invariant. And another technique is to think about the case where you are not able to do the operation and then classify which are the arrays on which you cannot operate. And while doing that, we already concluded that it is always possible to operate if the length is greater than or equal to 4. So now let's formalize this invariant. So we have concluded that invariant alternating sum of the original array is an invariant. So what does this tell us? This means that after doing the operation, remember that we were only interested in odd length. Why? Because the even lengths are trivial. You can always bring them down to 2. But for odd length, we were wondering that can we switch from 3 to 1. So if you had something like at the end, you will have remaining A minus B plus C, and you want to know whether you can convert this even further. So now notice that this alternating sum that remains at the end, this is S3, like let's say this is the alternating sum when you have just 3 elements remaining. Then the conversion from length 3 to length 1 can only happen if A minus B plus C is strictly greater than 0, or which in other words means that the alternating sum of the last 3 elements remaining should be strictly greater than 0. But we just said that no matter in what operations you do the no matter in what order you do the operations, the alternating sum doesn't change ever. So this means that whatever order you do the operations in the last 3 elements that remain, their alternating sum will not change from the original array. So if the original array of length n had alternating sum s of n, then S3 would be equal to s of n. This means that if the original array has greater than 0 alternating sum, so if it has a positive alternating sum, then it is always possible to convert it to a length 1, and order actually doesn't matter. So this is a big discovery, that if the alternating sum of this entire thing, if it is greater than 0, then when 3 elements are remaining, no matter in what operations you do, no matter in what order you do the operations, their alternating sum would be greater than 0, and their alternating sum is nothing but the criteria for determining if the operation should be done once more. And if you do this once more, you will be remaining with just one element in your subarray. So lots of big steps over here. So let's formalize all of these. So right now we have concluded that we already said that the alternating sum of the original array is an invariant, it does not change. So an array of odd length can be reduced to length 1 if and only if the original alternating sum is strictly greater than 0. Because if it is not strictly greater than 0, then no matter what strategy you take, in the last round you cannot do the conversion, because this sum will be equal to the original alternating sum, which is less than 0. In fact, you can also formalize this part that strategy does not matter. So this is very surprising. At first, it looked like that the strategy will matter a lot, so that the last element that you are aiming for, that does not end up not satisfying the criteria. But now we are making a new discovery that in fact the strategy does not matter at all. You can do the operations in any random fashion as long as you are allowed to do, and you will always have one window where you're allowed to do these operations if the size of the original array or the size of the reduced array is at least 4, and then you can either reduce it down to 2 or 3. But if you want to go from 3 to 1, then you have to check whether the alternating sum of the original array is strictly positive. If it is positive, then you can definitely jump from 3 to 1. So this is one version of the problem where you wanted to just find out whether you can, what is the minimum length uh, that you can reduce an array of length n down to while doing these operations. So this part also required a decent bit of observation skills. And what do you think the rating of this problem would have been uh, if it appeared in a Codeforces lead code or at Coder round? Do let me know in the comment section. And in the second phase of this video, I will be talking about some data structures and algorithm optimizations to this problem. Not exactly this problem, because this problem we have already solved in O of n. All you have to do is find out the alternating sum, which can be done in O of n of the original array. You can do it. So if the original array had even length, then the answer is 2. If it is odd length, then the answer is either 3 or 1. It will be 3 if the alternating sum is odd. It will be 3 if the alternating sum is negative, and it will be 1 if the alternating sum is greater than 0. Now we'll talk about the next version, and in this version we say let's define find all subarrays that can be reduced to 1, to length 1. So same problem as before, but this time you want to find out how many subarrays are there. Subarrays, not the original array. Right now we only solved this problem for the original array, and this time we are interested in knowing how many subarrays are there uh, that you can reduce the length down to 1. So how do you solve this problem? So notice that we already concluded that length 1 can only be achieved via two criteria that are being satisfied. And what are the two different criteria? Let's list them down. Criteria 1 is array, or I should say subarray length should be odd. Only then it can be reduced to length 1, because we said that the parity does not change. And what is the criteria 2? Criteria 2 is that the alternating sum of the subarray should be positive. If both of these conditions are satisfied, then the subarray that you are considering can always be reduced down to a length 1 subarray, no matter what your strategy that you select. So, but the problem is that there could be O of n square different subarrays. And if you check the alternating sum of each subarray, the time complexity becomes O of n cube. So how do we apply some observations and some known techniques to reduce the time complexity even further? So then you will notice that in these kind of problems, wherever you have to find the sum of a subarray, you use something known as a prefix sum. So can we apply the same prefix sum strategy over here? But this time things will be a bit different, because let's say the array contains these elements A, B, C, D, E, F and G. Now let's define the alternating sum, and let's assume one based indexing. This is 1, 2, 3, 4, 5, 6 and this is 7. Then you define it like so. You define prefix of I is the alternating sum. So that is basically 1 into A of 1, and then you add minus 1 into A of 2. You add plus 1 into A of 3 and so on. So basically at each stage I, you add minus 1 to the power whatever, minus 1 to the power something. This will be decided based on the index. So for example, if the index is odd, then you are adding 1. So you should add minus 1 to the power I plus 1 into A of I. So this is the alternating sum. So what would this prefix contain? So if you go by this definition, then the prefix 0 would contain A, and then it would contain prefix 1 would contain A minus B, then it would contain A minus B plus C. This is P1, this is P2, this is P3, this is P4, A minus B plus C minus D. This is P5, A minus B plus C minus D plus E. And this is P6, A minus B plus C minus D plus E minus F. Now, suppose if I give you a subarray, suppose I give you a subarray that starts at, let's say, this C, and this ends at, it has to be of odd length, okay? So let's say it ends at G. So how do you verify this condition for a subarray that spans from L to R? So first of all, its length should be odd. Its length should be odd. But what is the length of such a subarray? It is nothing but R minus L plus 1. So this quantity has to be odd. This means that if this is an odd number, then this has to be an even number. So R minus L should be even. So these are again some observations that we are making. And again, this might be trivial to some of you. So R minus L is even. Then what does it tell us about the parity of R and L? So you can say that the parity of L and R should be same. Only then R minus L could be even. So this means that if you are starting your subarray at an odd index, you have to end it at an odd index for it to be a viable candidate. So let's actually list that down as a criteria. So this is again some observation. Let me replace this and let's list down the observations that we have made. For us, for a subarray A L to R to be valid, L and R should have same parity. This is criteria 1, rewritten in other words. And what is criteria 2? It says that alternating sum of that subarray should be positive. But how do you find out the alternating sum of this subarray? So if you look at the segment from C to G, you are interested in this quantity. And the quantity is C minus D plus E, because you have to view it in isolation because you are solving it for that particular subarray, plus E minus F plus G. So how can you get this quantity from this alternating prefix sum array that we had defined? And this is where you'll have to make some observation. So this quantity, you will see that if you want to get, what if you take this entire big quantity that you used to do in normal standard prefix sum, you take this big thing, and this big thing would be nothing but, this is up till 7, right? So what will be prefix of 7? Let me write that down as well. Prefix of 7 is A minus B plus C minus D plus E minus F plus G. So you take this entire big thing and you write it down. So what is the big thing? So the big thing is A minus B plus C minus D plus E minus F plus G. And then you want this section only. So you want to remove all traces of this part. So you look at the prefix of L minus 1, which is this one, A minus B, and you subtract it. So you do minus A minus B. And then if you notice that some terms will cancel out, A and A will cancel out, B and B would cancel out, and the thing that you would have remaining is exactly what you are looking for. So C minus D plus E minus F plus G, which is what remains. So in fact, it looks like that the formula still works. That the standard formula for a subarray sum in normal prefix sum is what? Prefix sum of R minus prefix sum of L minus 1. So looks like that if you define the alternating sum via this manner, the formula would still work. But there is a catch, because right now you just started your subarray at this index 3. What if you had started it at an index 4? Or what if you had started it at index 2, let's say? So let's consider that case. So if you want to start it at index 2, and then you have to end it at index even, right? Because we said that L and R should have the same parity. So then you are looking for this prefix sum, B minus C plus D minus E plus F. So you start at 2 and you end at the same parity, which is 6. Plus minus plus minus plus, this one. So how do you get this number? Because to get this number, if you apply the same formula over here, like you compute P of 6, which is what? A minus B plus C minus D plus E minus F. This is P6. And then you subtract P1, which is prefix of L minus 1, which is what? Minus A. So after you do this subtraction, you will notice that A and A cancels out. But what you remain with is minus B plus C minus D plus E minus F. So you see that everything is opposite sign that you want. So in fact, subtraction is not the correct strategy. You actually have to do this prefix of R minus prefix of L minus 1 into minus 1, which is in other words nothing but prefix of L minus 1 minus prefix of R. So now you can see that this prefix sum trick to compute the sum of a subarray is almost still valid, but with some modification. So if you want to apply this trick on an uh, alternating prefix sum, you have to have these two rules. That again we write down that same criteria as before. This is the criteria 1. So L and R should have the same parity. This is the first criteria. And if L and L or L and R, since they are of the same parity, it actually doesn't matter. So you can say that if L and R are odd, then the alternating sum is So if they are odd, we said that if they are odd, then the formula is simply this: prefix of r minus prefix of l minus 1. And if they are even, if l and equivalently r as well are even, then the alternating sum is prefix of l minus prefix of l minus 1 minus prefix of r. So now, armed with this information, how do you compute all the subarrays that can be reduced down to length 1? So let's see how we can do that. So you define, let's define something like, this is a very common trick. Like now we want to apply a contribution technique here. So we want to apply a contribution technique, and you define dp of I as the number of subarrays that end at r and reduces to a one length array. So this time, instead of trying to iterate over all the possible subarrays, you try to fix the right endpoint, and you wonder, okay, if this is my right endpoint, how many subarrays can I create that end over here and have a positive alternating sum? So how do you solve this version? So how do you populate dp of I quickly? So how do you do it fast enough? So you are now looking for this r, and you want to know how many such l exist on the left hand side. First of all, l and r should have the same parity, so that is for sure. And then you want to know that in the prefix sum array that you have created, if r is odd, right? If r, suppose the current pointer that you are on, if it is odd, then you want to know how many integers on the left hand side of the prefix sum array, because if it is odd, then this quantity must be greater than 0. This means that prefix of r should be greater than prefix of l minus 1. This means that you are looking for how many elements are there on the left hand side that are strictly less than prefix of r. And how can you do that? You can, one strategy is to simply walk over each of these elements and then compute their count, and that would incur cost O of n for doing the DP transitions. But another fancy way to do it is you can use a segment tree or a Fenwick tree. But for using segment tree and Fenwick tree, notice that these prefix sums, right, they can become positive as well as negative. And in fact, if the array values are up to 10 to the power 9, then it is not possible to store all of these values in a segment tree, because segment tree can only support values up till 10 to the power 6. So then you can use another technique called coordinate compression. So you can use coordinate compression to reduce all the values from 0 to, or let's say minus 10 to the power 9 down to, you can map all of these numbers in this range, because the total number of unique integers can only be up to 10 to the power 6, which is the length of the original array. And notice that here you are only interested in the comparisons. You don't actually care about the value. You just care about how many elements are greater than something and how many elements are less than something. So if you do coordinate compression and then you use segment tree, then all you have to do is locate where is prefix of r in your segment tree. Suppose this is the prefix of r after doing the coordinate compression, and then you are looking for all the elements that are, how many elements are there that is to the left of it. So you just need to get the count of all these elements from here, and add your count to the answer. This is when the R that you have selected, that is odd. What about the case that the R that you have selected is even? Now, of course, when you are selecting this R as odd, you also have to ensure that L is odd as well. So you will maintain two segment trees, one for the odd indices and one for the even indices. So if you do that, then when you are investigating the even ones, then you have to look at all the elements on the left hand side such that prefix of L minus 1 is strictly greater than prefix of R. And in this manner, you can populate the DP value in O of log n via segment tree and coordinate compression, and then you can get all the DP values in total n log n because there are n dp values. And then what will be the answer? The answer will be simply summation of dpi, because dpi means how many subarrays that are reducible to length 1 and that can, yeah, how many subarrays that are reducible to length 1 and that end at particular index I. So all the subarrays that we are looking for, they have to end at some index, so you simply sum it up. So this is the easy, boring, uh, trivial solution. But I wanted to show you another trick where this trick I saw in the Codeforces comment sections. This is not something that is original to me. And this is what again requires some sharp observation skills. And with these observation skills, you will not need coordinate compression or segment tree or Fenwick tree to solve this problem. But it's a bit challenging to come up with. You can only notice that if you are actually paying attention to what's going on. So we'll try to see that trick on how to avoid using segment tree as well as Fenwick tree. So we'll have the same DP definition. No, we'll have to make some changes. So let me remove it over here. And now notice that we have two conditions. That is, if L is odd, let's write down these conditions formally. If L is odd, you want this to be true. You want prefix of L minus 1 to be strictly less than prefix of R. Okay, I have just added a greater than 0 sign over here and then transferred this over here. So prefix of L minus 1 is strictly less than R. But if L is even, notice that I'm not talking about R anymore because L and R are equivalent. We have already concluded that they will be of the same parity. Then you can see that you want this prefix of R should be less than prefix of L minus 1. Again, I did a greater than 0 over here and then sent this over here, and you can see that prefix of R is less than prefix of L minus 1. Now this is the part where you have to listen very carefully because it's not at all trivial to see what's going on. So first thing, we said that L and R should have the same parity, but now here we are observing a different quantity which is L minus 1 and L minus 1 over here. So what can you say about the parity of L minus 1 and R? So if L and R had the same parity, then this means that L minus 1 would have different L minus n. This would mean that L minus 1 and R have different parity. So, okay, now when L is odd, if L is odd, then L minus 1 is even. Now notice the minimum value. So we are only looking at two quantities, which is prefix R and one is prefix L minus 1. So notice the minimum value between them. So if L is odd, the minimum value is what? Prefix of L minus 1. and when L is even, the minimum value is prefix of R. But if L is odd, notice that this L minus 1 is even. But when L is even, R is also even. So what can you conclude? You can conclude that this is a very big observation that you can make. This is a big observation that the minimum value is always contributed by an even index. No matter what L or R is, the minimum valued contribution should always come from an even index. It's not at all clear from here, but when you do this math like this, then it becomes clear that the minimum value, be it P of L minus 1 or P of R, it always comes from an even index. And the maximum value, of course, will come from an odd index because L minus 1 and R have different parity. So then if you be smart about it, and then if you define your DP definition in a different fashion. So our previous DP definition was, what is the number of subarray that end at this location? But this time will be a bit sneaky, and we'll do something like this. Define DP of I to be the number of subarrays where A of I acts as the minimum element. So this time we are not saying that the DP of I means your array has to end over here. So this time we are only defining a DP for the even indices, right? Let me write that down explicitly. DP is defined only for even indices. There is no concept of DP for odd indices because an odd index can never contribute a minima. So if you define your DP like so, where A of I acts as the minimum element, then if I ask you to find out the DP value of this element, then you know that this has to be the minimum element X. Then you actually don't have to look at on the left hand side as well. You can look on the right hand side as well. And what you do is you have the original array which is not changing. You have this prefix sum array. This is not changing. So you get the upper bound. So this is the minimum element, right? So X has to be the minimum element. So whatever other candidate that you choose has to be greater than or equal to X. Now, of course, the maximum element can only come from the odd indices, and the minimum element can come from the even indices. So let us store all the all the odd indices in one array and sort the entire thing and keep it in a sorted order. Then, as we said that if you are considering dp of I, and suppose a of I is equal to x, the value at that position is equal to x, not a of I, where prefix of I should say. So prefix of I is equal to x, then you just find out all the elements that are strictly greater than x, because x is the minimum. So it will be some suffix, and this part you can find via the upper bound function from C++ STL via binary search basically. And then you can see that all of these elements, they will contribute to the final answer, because these elements that are strictly greater than it. So if you are finding out this, if this is the I that you're dealing with, then the elements in this section, they can either come from the left half or they can come from the right half. So how do you define this subarray? So then you be smart about it and you say that, okay, if it is coming from the left half, then and at that point of time I will act as R. But if it is coming from the right half, at that point of time this I would act as the L minus 1. So now you can see that you don't really have to do any coordinate compression or any segment tree, Fenwick tree, anything, because segment tree etc is only needed when you want to search on a prefix and then you want to append to that prefix. But here we are searching on this entire array. So with just some smart transformation that we have done, this problem turns into searching on a static array, and that can be simply done via lower bound and upper bound. So just to summarize what we have done in this last part, we take this DP definition, and DP of I is the number of subarrays where prefix of I acts as the minimum element, and DP of I is only defined for the even indices. How do you populate DP of I? So you can see that if you want to populate DP, you can do something like DP of I is equal to collect all prefix values at, so this DP is only defined at the odd indices and you want to pair it up with an even index. Why do you want to pair it up with an even index? Because remember that we are only locating L-1 and R. We are only locating L-1 and R. So L-1 and R will have different indices, right? Different indices parity. So you collect all the prefix values at odd indices, sort it, then the count of elements that are strictly greater than prefix of I in this sorted array is the number of subarrays in which prefix of I acts as the minima, and your final answer would simply be your final answer would be summation of DP of I for all the even indices. So now you can see such a clever solution this is, right? No fancy data structures, and all of this can only be accomplished if you kind of sit with this problem and then think about it for a while, right? Otherwise, if you're just looking to spam some data structure to solve it, sure, it can be done, but this solution, like, I found it really creative, really unique, and that's why I decided to make a video on this, even though this is not original to me. And I think this, like, accurately captures the spirit of competitive programming, that you are spending some time with the problem and then you are coming up with unique ideas to solve it, that is a bit different from the editorial. And even though it might not necessarily be required, because in this age, like, you have all your tools at your disposal, right? Like, if you have segment trees and if you have Fenwick trees available to you, why do you want to make it more complicated? But then it is nice to sometimes slow down and think about things from a different perspective. So just this transition alone, like having a normal DP definition where you define DP of I as the number of subarrays ending at R, to going to this creative definition where you want it to be the number of subarrays where this element acts as the minima, that itself is quite fascinating. So this was it. I will link down this problem in the comment in the YouTube description in case you want to solve it. And if you had any other approach, or if you also arrived at the same conclusion that you don't really need segment tree or Fenwick tree, do let me know in the comment section. Or if you had any other intuitive approach to reach the same conclusion of why alternating sum comes into picture and how to spot these invariants, do let me know in the comment section. Thank you.